Hello everyone, hello professor. My name is Trinh and today I and Fu will talk about human level control to deep reinforcement learning, which is a very influential paper from DeepMind published in 2015. And this paper will introduce about deep Q network, which is DQN, and it will be the very first system that achieve human level performance on many Atari games using only raw pixels as input. So this is what we will cover. We will cover the motivation, the Atari environment, Q-learning, deep Q network architecture, stabilizing techniques, key results, limitation, and takeaway. So firstly, about the motivation, the goal is to create one single algorithm that may learn many tasks from raw pixel, and that means that with one single model, it can play many different games without rewriting the model for each game. This is challenging because like Atari game had high dimensional input, which is the raw pixel as you can see over here, and it rely on handcrafted features. So old method it rely on this handcrafted feature. It need like user input, so we want to learn them automatically with very minimal prior knowledge. It also partial observability, so a single frame will lack motion info when we play the game, like the velocity or the direction. And it also depends on long term because of the reward. The reward come much later. So Atari games stay very messy, so it is impossible to kill learning, and traditional Q-learning can handle it because it needs a good state representation, and we need a function approximator to estimate the Q value instead of storing them. So DQN will try to solve it. So about the Q-learning refresher, this is the Q-learning. So Q-learning tries to learn a function that tells us how good an action is in a given state. It updates by this formula, and this causes problem because it's unstable with neural network. The first one is the correlation between the frames. So in a video game, sequential frames are highly correlated, which cause the network to learn them to become overfitted and fail to generalize. And the second is because of the moving targets. Unlike supervised learning, when the target is in Q-learning, the target value depends on the network always. Updating the way will make the target immediately change and causing the training to unstable and unable to converge. So the question is why DQN? DQN has many advantages. The first one is no handcrafting. So DQN can learn successfully policy directly from high-dimensional sensory inputs like pixel and score to action, and it requires only minimal prior knowledge. So the second one is generalization. So it only use one model and use only one the convolutional neural network to extract spatial features. And the third one is the performance. So the performance of DQNs is very better than other algorithms, and it also comparable to human game tester in 49 games. So about the deep Q network, the input is 84 times 84 plus 4 frames. So this is the layer, and the output will be the Q value per action, like left, right, and 5. And the question is why 4 frames? Because we want to track like the velocity and direction. So choosing the most 4 recent frame will allow us to get to know that.
Hello everyone, I'm Fu, and this is the heart of the paper, the key tricks that made DQN stable. And this is arguably the most important slide. And to solve the instability issues we just discussed, the authors introduced 3 key innovations that make the deep reinforcement learning work. First one is experience replay. Instead of learning from consecutive frames, which are highly correlated. The agent saves its experience into a large memory buffer, and during training, it samples a random mini batch from this buffer. Think of this like studying for an exam and using shuffle flashcards instead of reading a textbook page by page. And if you read the textbook in order, you might forget the chapter 1 by the time you reach chapter 10. Shuffling will break the correlations and ensures the agent doesn't overfit to what you just saw. The second, target network. We notice the equation compare two values, the prediction, the red part, and the green part, the target network. So prediction, it uses the current weight of the main network, and this is what we are training and updating at every step. And the target, this uses a separate network called the target network, and crucially, its weights are frozen. We only update them every few thousand steps. We freeze it to stop the target from moving while we learn. Yeah, it will solve the chasing your own tail problem. And the square, this shows we are simply using mean square error, MSE, just like in a standard regression problem. And because we want to minimize the error to pull our prediction, the red one, closer to the target one, the green one. So without this, Q-learning is like a dog chasing its own tail. The target keeps moving as we learn, and by freezing the theta minus the target network, we keep the target stationary for a while and allowing the main network to aim and converge stably. The last one, reward clipping. Finally, different archery games have vastly different scoring systems. Like Pong, it gives 1 point, and while others give thousands. And to handle this, the authors clip all positive reward to positive 1 and negative rewards into -1. And why it matters? Because it will limit the scale of error derivatives, allowing the same learning rate and hyperparameters to work across 49 different games without exploding gradients. And together, these three techniques transform unstable neural networks into a robust agent capable of human learning control. Next, the author will test the agent on 49 archery games. In the arcade learning environment, the key point is the same network, same hyperparameter for all games, and no game-specific engineering. The only inputs are pixel frames, game score, and this demonstrates a generality of the method. Next, DQN achieved impressive results. It outperformed previous reinforcement learning methods in 43 out of 49 games, and it reached a human-level performance in more than half of the games. It learned meaningful visual representations. The most impressive part is that it did this just from raw pixels, no handcrafted features. A great example is breakout games. At first, the agent plays randomly, and then it learns to hit the ball repeatedly. Eventually, it discovers the high-level strategy of digging a tunnel into the top, so the ball will bounce behind the bricks. This is a long-term and non-trivial strategy. It learned entirely from the reward signal. So, despite of the success, DQN has limitations. It performs poorly in sparse reward games like Montezuma's Revenge because they know immediate feedback, and it's still limited in long-term planning, and its training is computationally expensive, and it uses millions of frames of a gameplay to learn what humans learn quickly. These issues inspire a layer improvements such as A3C, Double DQN, and others. And to summarize, DQN was the first deep reinforcement learning system to reach a human level control from raw pixels. And the key innovations are CNN features, experience replay, and the target networks. This paper laid the foundation for modern deep reinforcement learning, including AlphaZero, AlphaGo, Deep Mind Control Suite, and more. This is why the paper is considered a milestone in AI. Thank you, Professor, and thanks everyone for listening.